Hello and welcome to our channel again. So here I am Suraj with a new video of mine on the series of our quantum mechanics lecture. So in the past lectures in quantum mechanics, we have dealt about different types of potentials, which is the infinite square well and the basics of the quantum mechanics. Now we are going to study some deeply in the quantum mechanics, which is solving the Schrodinger wave equations for different types of potentials. So infinite square well is a very simple potential because the potential is zero inside the well, and at the wall's boundary, the potential is infinite so that the particle can't escape from that. But now we are going to deal with some of complex, situations of the quantum harmonic oscillator where there is a potential of the particle which is not a zero, Okay, so we are going to discuss about the quantum harmonic oscillator. So before deep dive into this, I will try to explain what exactly is the classical harmonic oscillator. Okay, so you have heard of the harmonic oscillation, SHM. Okay, so in class 11th, if you are study, then in class 11th you see that you study the SHM, which is the simple harmonic motion. So in simple harmonic motion, this is very simple, that there is a particle who is moving at a plus extreme and the negative extreme. This is the plus extreme and this is the negative extreme again and again. Okay, and we have to analyze its motion such that there is a force there, such that there is always a force which is the negative direction of your displacement, which is trying to just stop. Suppose that there is a particle starts moving, so when we start pushing it, we first push it, there is a force F is equals to the minus kx, which has started applying some force to just move it to the backward to the mean position. And when the effect of our force becomes zero, it is moves again in the opposite direction, then comes to the mean position, then to the negative extreme, and this motion's always okay. So what we have to do is that in the classical harmonic oscillator, we have a very important equations which can determine the analyze of the motions of this particle. If you have remember, then x of t can be equals to the is equals to the a sine omega t, a sine omega t. So this is a very famous equation in the SHM you study, which is used to analyze the motion of our particular particle. It is used to determine the distance of our, or use of displacement of our particular particle xt at any given time period t. Okay, where a is the amplitude of this particular particle, which is doing amplitude means mean positions, maximum distance from mean position it can cover is the amplitude of that particular particle, and sine omega t, where omega is the angular frequency, and angular frequency omega is equals to the 2 pi f, where f is the normal frequency. So this is the formula of the omega 2 pi f. So this is a very beautiful equations which governs this particular motion, analyze the motion of our classical harmonic oscillator. One example of the classical harmonic oscillator can also be a spring, a block which is connected to a spring, and we stretch the spring. When we stretch the spring, or when we contract this our spring, there is some sort of force which is started pulling it to its mean position, and there is also the potential here. So the best example is that if a spring, you can draw here, that I can analyze the motion. Maybe the diagram is not that much good, but this is a spring and the block is connected here. Okay, so if you, this is a mean position, so if you push it at some distance x, there is some of the potential energy stored which is now get converted into this kinetic energy. So we have a formula to determine the potential energy stored for any length we stretch it, and the formula is v is equals to 1 by half kx square. So this is our expression for calculating the how much potential energy is stored in a block when we just move it a particular x distance. Okay, so this is the formula for calculating the potential energy in the spring. And the kinetic energy is also the same expression in the spring force, but we have to not deal with the kinetic energy. The main theme is the potential energy for any arbitrary length x. And this is all about the classical harmonic oscillator. We are not going very deep into the classical harmonic oscillator. Maybe when I start the series on the class 11th physics, we will discuss about this particular SHM, simple harmonic motion, and also the motion of a block when it's attached to a spring. So these are very simple, there's not very much more complexities. But when we are dealing with the quantum harmonic oscillator, the things become very, very complex. Okay, so that's why this topic is very big. We have to put out the value of potential in the Schrodinger wave equations and deal to find out our sufficient wave functions that could describe our motions or that could describe anything about this particular particle. But in the classical world, this is not things. You can determine its position. And if you want to determine its velocity at any particular time period t, you can also find it. You can also find our velocity. So what you have to do, you have to just differentiate this function with respect to the time. And you will got this. So this is very simple in the classical harmonic oscillator sense. You cannot predict anything. Okay. So now we are going to deal with the quantum harmonic oscillator. This is all the talk about our classical harmonic oscillator. So let's move out towards the quantum harmonic oscillator. So in the quantum harmonic oscillator, we also have a potential. Okay. So the potential that we have to solve our the Schrodinger wave equation is potential is equals to the 1 by half m omega square k square. Okay, sorry, k square, m omega square. Oh, sorry, m omega square x square. Okay, so this is our potential of our particular particle which is moving in a quantum harmonic oscillator or whatever it is. Okay, so this is our potential for which we have to solve our Schrodinger wave equation. So let's write here the Schrodinger wave equation, putting out the values, and we have to solve it. So we can write as minus h cut square divided by 2m. Okay, and I want to tell you that we have to write the time independent wave equation, not the time dependent. Okay, why? I've explained in a previous video that why it is important to use, because it reduces the complexities, and also we can find out our time dependent from time independent very, very easily. That's why. So to avoid complexities we have to deal with it. Okay, that's why I put here the normal derivative, not our the partial derivative, because partial derivatives for the two function, but this is not a two function. Okay, then v psi is equals to the e psi. Okay, so this is our what equation become. So what we have to do is that we have to put our values of the potential here. What value of potential? So the value of potential is equals to the 1 by half m omega square x square, and we have to solve it. So now this is pretty easy to evaluate this, but remember, this solution is quite complex. Okay, so it may take more than one videos to complete this. So now let's plugging the value of our potential as minus h cut square divided by 2m. Okay, and here is d square psi divided by the dx square, and the plus here value of potential is 1 by half m omega square, and here is k square psi is equals to the e psi. So this is our what equation become, and we have to solve it. Okay, so there are various methods to solve this, and there are generally two methods. There are generally two methods that we are going to solve with it, but in this video we are going to discuss with a very important known as the ladder operators. Okay, ladder operators. So this is our first method of solving by using the ladder operators. What is ladder operators are? So we are going to discuss there, and there is also a second method which is which is generally not the algebraic method, you can say that, but this is an algebraic method and ladder methods, and maybe in the next videos we are going to discuss about our second method for solving our this harmonic oscillator. But now we are doing with our ladder operator scenarios, all the algebraic method. Second method is also very, very useful, but generally what we encounter is that in books generally there is a first method given, because the first method is very, very good, and it proves some of very important phenomena in the quantum mechanics in the quantum harmonic oscillator. That's why we generally choose our first form. Okay, so now let's start our solving this particular wave equation. Okay, so what we can do here is that we have to factor out something here. Yeah, we can factor out something here, because factoring out can help us to evaluate next. So how can we factor this? Okay, So let's factor out this result. Factoring is very important because if we factor is, what we get is that very important things. And these things can also do applying our ladder operators. So we have to factor out this particular formula to applying our the ladder operator scenarios. Okay. So we have factored out it very perfectly. And if you plug in the value here, you will get that this is equivalent to this expression. But we factor out because to apply some of our very beautiful formulas in the quantum mechanics for the harmonic oscillator. Okay, so here P cap is equal, P cap means the momentum operator is square. So if you square the momentum operator, it is exactly equals to the minus h cut square d square upon dx square, and you can see here that this is exactly equals to the this. And if you just multiply it, this m and m will cut out, and this expression is exactly similar to this equation. So what I do is that we just factor out it. Okay, now what we can see here is that, can I write this particular expression? I want to say that, can I write this particular expression as the Hamiltonian? Yeah, this is Hamiltonian. If you remember, if you remember my one of my lectures, I've said that the Hamiltonian psi is equals to the E psi, and it is an eigenvalue equation. So you don't know the eigenvalue equation, but in the next videos, I will explain the eigenvalues and eigenfunctions, etc. But for now, you can generally think that H psi is equals to the E psi. It means this particular expression is equals to the H. So can I substitute the values? Can I write here in a more good way that the Hamiltonian operator is equals to the 1 over 2m, and here our p cap square plus m omega x and x square. And here, yeah, this is what our equations become, that a Hamiltonian operator is equals to 1 over 2m p cap square plus m omega x whole square. Okay, so this is our what equations become. So now we are going to apply the ladder operators, and be careful analyzing these things, because now from here onwards our equations become some complex, and you have to see very carefully. Okay, so what we can do is that we will assign a operator. So let me write it form that in a complex world generally you can say that because of quantum mechanics is a complex world, wave function is a complex. Okay, so we can write that u square in a more suggestive way, that any number which is u square plus v square can be written as the iota u plus v, and here is a negative iota u plus v. I think I have remembered is, yeah, I think this is the, okay, so iota u plus v. Okay, this is exactly the thing here. U square v square is equals to the iota u plus v and negative iota u plus v. Okay, so can we write this here? Because we are dealing with the complex words, but when you multiply it, what you certainly knew that these equations become u square plus v square. So can you think that here p cap square plus m omega square is equivalent to the u square plus v square? But remember, these are not the, but I am assuming that u and v are of numbers. But here p and n omega x square, here p is an operator. Here p cap is an operator. So we have to think it, but we can write in this form. Okay, we can write our this particular expression in this form. Now see here. Now see, we can write the ladder operators minus plus is equals to the 1 over root under 2m omega h cut. So there's a whole root here. Okay, omega h cut minus plus iota p cap plus m omega x. Okay, so here what I have written here, what is this? So here a minus plus is the ladder operator. Minus plus is a ladder operator. So what exactly the ladder operators in quantum mechanics are? So ladder operators in quantum mechanics are generally very useful in increasing the energy of our system. Suppose that there is a energy E of our particular system, and if we apply our ladder operator, so there are two types of ladder operators, A minus you can see here and A plus, and both have different work. If we apply A plus ladder operator to any energy on any system, the energy of the system increases. But when you apply this particular A minus, which is known as the lowering operator, to a particular system, the energy goes decreasing and decreasing. But here A plus known as the raising operator and A minus is known as, here the subscripts A minus and subscript plus. Okay, so these two ladder operators are very useful because these are used to increase or decrease the energy of our particular system. That's why they are known as the ladder operators, because just like the ladders, when we step off to the ladders, we climb it and giving higher and higher, and that's the work of the A plus subscript A plus here. This is known as a raising operator, and A minus is known as the what operator? A minus is the lowering operator and A plus is the raising operator. So these operators are very useful because when I take the product of this A plus and A minus operator, we can easily find out very important expressions for the quantum harmonic oscillator. So here A minus and A plus is the combination of both A minus and A plus. So suppose that we multiply A plus and A minus, what will happen? So A plus and A minus has nothing, but they all only have the change of the sign here. In A minus there is the negative iota P cap, and in A plus there is positive iota P cap. And what we can write is that the multiplying by this, our root and root will cut out, and our this expression become 2m omega h cut. Okay, and here iota p cap plus m omega x, and here you can see that negative of the iota p cap plus m omega x. So after multiplying this, we got our expression like this. Okay, and now what we have to do is that we have to multiply it. Remember, I take the ladder operators because these operators are very useful, and they increase or decrease the energy of a system in the quantum mechanical system of a quantum state by applying A plus and A minus. Okay, so I assign the value of A minus, A plus, and multiply it, and multiplying it I got 1 over 2 m omega h cut, and here what's our expression becomes. And you see that this is similar to this and this. It means naturally if we multiply this, we got this. A lowering operator multiplied out the raising operator. Now what we can do, so we are going to multiply it. So multiplying out this expression here, what we get is that this expression becomes A plus A minus is equals to 1 over 2 m omega h cut. Okay, and here multiplying it by, what we get is that iota and iota becomes negative iota, and this negative become positive, and here it's become p cap square. Okay, here it's become p cap square, plus you can think this will become, okay, iota p cap m omega x. Okay, and generally this is now negative iota p cap m omega x. Okay, and this our expression becomes, okay, this our expression plus m omega x whole square. So this is our equations become when we multiplied it. So if you think this is plus iota p m omega x, and this is minus iota p m omega x, this is m omega x, and we just cut out, and what we can do is that we can just cut out here, but no, we can't. There is a mistake here. Sorry, there is a mistake. Here is very importance of the order of measurement in the quantum mechanics. Uh, okay, so what we can write it here is that negative m omega, yeah, negative m omega x iota p cap. Yeah, so this is our what equations become. And now we are going to discuss a very important thing. So if you watch my videos on the canonical transformation in quantum mechanics, you can easily think that what here this heck is. If you have studied, if you have studied it, then you can think that what this heck is. This, okay, this is very important. This result is very, very important. So stick to this result. And what we can now do is that this is the results of the canonical transformation. That there is an order of measurement and the iota, or you can think that the x p cap is not equals to this and this. So I think you have heard of it. And I have also made a video, so you can check out that video and know what exactly I am saying if you feel unfamiliar with the canonical transformation. Okay, so let me write it. A plus a minus is equals to the 1 over 2 m omega h cut. Okay, so let's this and this at the same thing. P cap square, sorry here, p cap square, this is a square sign, p cap square plus m omega x square, and here plus iota, I will write it here, I am omega, comma I am omega, this will become x of p, and this is the minus, sorry here there is will become not x of p, there is a error here, this will become p of x minus x of p. And generally, okay, now this is what our equations become. So let's take a look here. What is this? What is this? So if you have studied the video, this is the canonical transformation, which says that the x and p operators are not exactly the same. It means applying p operator to the x operator is not same as applying the x operator to the p operator. X operator to the p operator, and this is an uncertainty. There is the p and the x operator. It means the momentum and the position operator do not show the commutation relationship between each other, and the value of this particular quantity is equals to the iota h cut, iota h cut. But here I have written it p of p operator x minus x operator p, but generally it is xp operator. It means xp minus px. So I have to rearrange this term so that it becomes very, very good. Okay, so I have to rearrange this term, and what we can now think is that a plus, I am rearranging here. Okay, I am rearranging the term here, because if I do not rearrange the term, you will confuse between the minus and the plus sign that I keep. Okay, so I'm going to erase this. I'm just rearranging the term because to avoid the complexities, okay? Because if I do minus and plus sign changing, you will confuse that how I change the sign of minus and plus. Okay, take this first, okay? Take this particular expression first. What we got is that iota m omega x p cap, and here if I take the minus p cap x, Okay, now this things very look familiar, because if we have a look at my one of my lectures, the x of p is equals to xp minus, there are operators, okay, px, and this is exactly equals to the iota h cut. Wow, okay, so this is exactly equals to the iota h cut. It means this particular value is equals to the iota h cut. Okay, now what we can write is that a plus a minus is equals to the 1 over 2 m omega h cut, and here p cap square and plus here m omega x whole square. Okay, so m omega x whole square, and this expression is exactly equals to this iota h cut. And doing all of that things, what we can get is that minus and minus will become this, and yeah, okay. So whatever these equations now becomes is minus minus iota and iota become -1, and minus minus will become plus, and our expressions can be written as, so here iota and iota, okay, so iota and iota will become negative iota, and negative negative become positive, and if it's become positive I can write it here positive h cut m omega h cut. So this is our what our equations become very simple. And what if you can identify, if you can identify this particular expression 1 over 2 p cap square plus m omega x square is what equals to the Hamiltonian, what equals to the Hamiltonian, yes or not? Yeah, this expression becomes our Hamiltonian. It means what we can write it here is that a plus a minus is equals to the 1 over 2m p square is a Hamiltonian. It means Hamiltonian operator divided by the h cut omega, and plus m omega h cut will cut out is equals to the 1 by half. So this is our what equations become. So in the, so this is our what equations become. And remember, in our next video I will discuss the next part of this, okay, because this video becomes too long. In the next video I will discuss about how to evaluate this particular thing, and we reduces our this particular term, so you can say we quickly evaluate this term to the simplest term, and we can apply this to our considerations, and we can take this. So it take might one video more to just complete our derivations of our wave functions to solve our Schrodinger wave equation. Okay, so this is our video on the first part of the quantum harmonic oscillator. As I have said before that this is very complex derivations, and that's why it takes a very much mathematical. So in the next video what I am going to discuss is that to evaluate this derivations, and in the next video finally we can derive our expressions, finally we can solve our Schrodinger wave equations, and in another next video we can discuss some properties of the harmonic oscillator. So this is my today's video on the quantum harmonic oscillator. So thank you for watching my video.